in addition to the 3-address code, which represents what the program will do, we represent array references as matrices, which makes it convenient to analyze if there are dependencies or not. Okay, so we simply take the coefficients for each loop index variable and put it in a matrix. And in addition, we use an offset vector to take these constants. Okay, so an array reference is a variable, a matrix, a vector with loop index variables, this matrix plus the offset vector. And what we want to do to determine if there are dependencies between iterations in a loop is to take two different array references and check if they can access the same memory location. Okay, so how do we do that? Well, we need to solve this equation. I mean, this equation, the left-hand side is the set of matrix elements which what this reference will access, and the same for the right-hand side for the other reference. So I1 and I2 are the loop index variables. Suppose we have two loop index variables, I and j. Then there are 4 unknowns in this equation. 2 for the left-hand side and 2 for the right-hand side. So there are different instances of the loop index variables. And we solve for an integer solution. If we can do that, then we can find that there is a dependence with a certain distance, and this distance is the difference between the two iterations with which have a solution. Let's look at an example. Here we have 3 references, ABC, with these matrices and vectors, and there is a dependence between A and B, and also between A and C. And obviously they access the same memory location. I mean, they can, they're not in, well, okay, they can do that. And I mean, B is one iteration of the I loop behind A, and C is one iteration of the J loop behind A. So the distance vectors, recall, the dependence distance, this is a vector. It's the difference between these two vectors, and for A and B it's this one, and for A and C it's this one. So we have a set of dependence distances. This set is represented as a matrix as well, but and this okay, so it's a set, but we represent it as a matrix, which means we can change the order of the rows as we wish. It's just that we have selected to store it in a matrix. And also, if there would be additional references with identical dependence distances, we would only keep one of them. The dependence matrix, it collects and shows us all the dependencies for a particular loop. And if there are dependencies in this I mean the first column corresponds to the I loop and the second column corresponds to the J loop. And if there are dependencies, the first non-zero element on a row, it says there is a dependence in the corresponding non-zero loop. So this non-zero, it says that there is a dependence in the I loop, and this non-zero says there is a dependence in the J loop. Okay, so to parallelize this loop, we cannot run either of the loops in parallel. What we would like to do is to change the order of the loop iterations without violating dependencies, of course, so that we can exploit either vectors, I mean sim vectors, or software pipelining, such as modular scheduling, or a multi-core to run the outer loop in parallel. Okay, so how can we do that? We can use a so-called unimodular transformation to change the order of the loop iterations. Of course, it's the same loop iterations, otherwise we would change the behavior of the program. But we execute them in different orders, in a different order. How we will do that, we come to later in the course, but this is really neat. Okay, so loop parallelization. We can parallelize inner loops for modular scheduling or software pipelining in general, and vectorization, such as for SIMD instructions, and outer loops for parallel computers, that is some kind of multi-core machine, such as a shared memory multiprocessor. Okay, the last slide for the first lecture. We have a Optimizing Compilers Hall of Fame at Lund University, which is all the winners of the Optimizing Compiler competition since the first time the course was offered. Okay, and well, you may recognize some names here, possibly. And this might be you for the next course occurrence. If you win, there are groups of 1 or 2, you will win eternal fame and a coffee mug. Okay. More about the competition later.